Well, good morning, folks. How many of you guys had to help your parents shovel today? Just one, two, three? Okay. Good for you. You are good sons and daughters. So, serious question. Okay. Do you know any cannibals?
Yeah, of course. You know?
Okay. Oh, I do. And I was wondering the other day, why is it that the cannibals I know, maybe the cannibals you know, Emma, are like this too, they refuse to eat clowns?
Why?
Anybody know why it is that most cannibals refuse to eat clowns?
Because
They
they taste funny.
taste funny. Happy Tuesday. On a lighter note, why is it that the guy who was really into tennis, he only bought 9 rackets. He refused to go anymore. He would not buy 10 rackets. Why is that?
That's just too many rackets.
It would be. You are right. 10 is too many. Oh boy. And you are officially prepared for the test tomorrow.
No.
Okay.
Is that going to be on the test?
It should be.
Energy?
I should put that as a little bit of extra credit.
Yeah, that sounds even Can we also do that for our final? Just like give a presentation to the class of our best dad jokes?
Right. Well, the final has a lot of jokes on it. If you remember, the first semester exam had, letter D were some pretty fun answers. There might be a couple dad jokes on that. But all right, so I suppose we got to do a little bit of studying. And the test will be tomorrow. Folks at home, hopefully you can check this out on Schoology and be caught up so that you don't have to make up the test later. So, loosen up your hands. We're going to be going through some practice problems for this test today. If you feel like it, you can write this down too. This will be the key that you'll be using to answer questions on the first page of the test. And what we'll be comparing in this example is we'll be comparing what happens to the acceleration of this object if we change a couple things about what's going on here. So you can see there's a mass, it's got wheels, and it's being pulled by a tension force off to the right. And, of course, because of that, it's going to have some sort of acceleration because there's no opposing force to the left. So it will have a certain acceleration. Question 1 might be, what happens to the acceleration if we change the angle of the string? So now it's the same tension force, but it's being pulled up at some angle. So how will that change the acceleration compared to when it was just pulled straight across? So tension force would be the same number, maybe it's 10 or something. So now instead of 10 going straight across, it's 10 going up at an angle. So which letter do you think we should put for this one? Will the acceleration now be greater than, less than, the same, or there's not enough information to tell compared with how it was originally? How many votes do we have for it is bigger?
Excuse the interruption. Mr. Kazmierski, please go to room 116. Mr. Kazmierski, please go to room 116.
Any votes for it being lesser? Any votes for it being the same? Not enough information. Good. It is going to be lesser because, as you figured out in your heads, the force is now going up at an angle. So the amount of force that would be going horizontal is going to be less because some of that force is now going up. So indeed, the acceleration will be less for that type of an example. Let's say that we are no longer pulling up at an angle. But now the cart is actually sitting on an angle. And it's being pulled up with that same tension force there. So compared with when it was flat, being pulled horizontal, how many people believe that the acceleration will be greater? That's good. How many people believe the acceleration will be lesser? That is also good. Yes, it is going to be less because now, yeah, it's being pulled in a straight direction, kind of, but now you've got gravity opposing that. So the acceleration is going to be determined basically by comparing this force and this one. And now that we're subtracting some force from that, it's going to be a smaller acceleration. Very good. Let's say we go back to normal. It's on a flat surface, being pulled to the right. But what we do now is we decrease the mass by 1/2. So if it was originally 10 kilograms, now it's going to be 5. So what is that going to do to the acceleration? If you believe it's going to make the acceleration greater, raise your hand. That's perfect. Yes, it's going to be bigger because F equals ma. In this example, tension force is mass times acceleration. So if I go ahead and decrease my mass, keeping the tension force the same, the acceleration is going to go up and compensate for that difference. Very good. What if we do the same thing? We take the mass of the cart and we decrease it by 1/2, just like the last time. But we also decrease the tension force by 1/2. So now we've got two things going on. You believe the acceleration will be greater? Raise your hand. Lesser? Raise your hand. The same? Raise your hand. Perfect! Boy, you guys are going to nail the first side of this test. Because, yeah, tension force equals mass times acceleration. So we're decreasing this by 1/2, and we're decreasing this by 1/2. Then those two things offset each other, and this acceleration is going to remain the same value. Very good. That's the sort of thing to expect on page 1. Page 2. Hey, Trey. Thanks. Go ahead and draw this. Now, I'm well aware that this was the last chapter, and we thought it was in our rearview mirror, and it is for the most part. I just want to, this type of a graph, velocity time graph, has a lot to do with forces. And so we want to touch on this at least briefly on that test. So what you're going to be asked to do is to recreate the two other graphs, position time and acceleration time, but it's just going to be for one of these intervals. The other thing I'll say is that it'll always be in the positive side of the velocity time graph. So there's really 2 or 3 different ways that this graph would go. It's either going to be going up, it's going to be going down, or it's going to be going across. And that's in the positive section. So there are really only 3 possible solutions to this. And we'll do the one where it's going up here. Maybe we'll do the others too. So on a position time graph, we start with some velocity right here. We'll say that I want to put C to D on my position time graph. If I want to put just this portion on the graph, then I got to realize that at this point I've got some sort of positive velocity. And so on my position time graph, that means I'm going to start with a slope that's kind of positive. As time goes on, velocity grows. So as time goes on, our slope will grow. So it might look something like this. Curving up. Now, even if you have no idea how to draw your position time graph, you should definitely get the acceleration time graph correct. Because your acceleration time graph is just determined by the slope of the velocity time. The slope of this tells you acceleration. Is this a positive, negative, or slope of 0? Positive, absolutely. So we have a positive acceleration. And that's all there is to that one. And let's just, for the sake of it, might as well cover all of our bases. Let's just say that this was going down instead of going up. So if it's going down, that means I would be starting with a high velocity, and as time goes on, the velocity would be decreasing. So I'd have to start with a big positive slope that decreases over time. So the other option for this, if it was going down, would be something like that. What you're going to see on the test is going to be one of those two. You're either going to be drawing a half happy face, or you're going to be going, high slope to small slope. Okay. Of course, the acceleration for that, if it was going down, it's negative, your acceleration would be 0. Okay. Questions on what's going to be expected for this? This is the last time you'll see these graphs, I promise. So now the other question might be, what's actually going on at each of these intervals? So from A to B, you can see we begin with a velocity of 0, so we're starting at rest, and then the velocity grows in the positive direction. That's really all you'd need to put if I was asking you what's actually happening. You start from rest, and the velocity grows. If you want to be specific, you could say it's growing in the positive direction, you're moving away from the origin, but I'm not going to be grading this real critically because this isn't our actual chapter that we're mostly focusing on. From B to C, anybody tell me what's going on from B to C? Constant velocity, exactly. You will see something like this for this example on the test. Resist the urge to say that it's holding still there, because it's not. If this was a position time graph, it would be. But as Emma said, we have a constant velocity. Whatever velocity this corresponds to over here is the velocity you have for that entire interval. Then, of course, from C to D, you're speeding up again, and that speeding up is going to be a faster rate of increase than this one right here, because the slope is larger. Which kind of brings us to the next question. Where would you say the magnitude of your net force is the largest? We've got 3 options, A to B, B to C, or C to D. Any guesses? Where is your overall net force the largest here? How many votes do we have for A to B? B to C. C to D. That is perfect. Yep. Because we have a bigger slope. And the reasoning follows that on a velocity time graph, your slope represents acceleration. So if you've got a bigger slope, you've got a bigger acceleration. And if you've got a bigger acceleration, you're going to have a bigger force. So yeah. Is your overall net force equal to 0 anywhere? And if so, where? It is. Is it from A to B? Is it from C to D? Is it from B to C? Absolutely. Because if you keep a constant velocity, you have a net force of 0. You could have friction, you could have an applied force, but those things are exactly offset if you're not changing speed. And that's what an overall net force of 0 would mean. So good. Yeah, write down whatever you need to make sure you know that information. This is pretty much what page 2 is going to be like. All right, time to deal with some actual force diagrams and force equations here. And this is going to be on page 3. All right, so you can probably guess what I'd like you to try and figure out from this one. We know the acceleration, we know the mass, we know the coefficient of friction, and actually, I'm going to get rid of these wheels. There shouldn't be wheels on this. It's dragging across the floor. So the only thing we don't know is tension force. What I'd like you to do is take a minute or two, see how far you can get with this, and then we'll go through it together. Again, you're looking for tension force. Anybody get 33.7? Cool. All right. We'll go through this together, and then we'll move on. So if I want to figure out my tension force, I'm going to use the exact same procedure I use for every other force problem, whether it's this chapter or the inertia chapter. Do a force diagram, do a force equation, and then solve. Even if you're solving for a force, because most often we're looking for acceleration. So even though we're looking for something different than what we're used to, we follow the exact same procedure. So, force diagram, I'll just say what it is. You've got gravity down, normal force up, tension force this way, and friction to the left. So, if we're looking for the tension force, it is a horizontal force. So I want to make a force equation for the forces that are going in the horizontal direction. So horizontally, we've got tension, we've got friction, and those are going to equal mass times acceleration. If I want to figure out my tension force, I'm going to isolate it in this equation. So these two are good. I know mass, I know acceleration, and we have to remember what force of friction is equal to now. Force of friction is equal to coefficient of friction times normal force. And in this case, we're on a flat surface, and there's nothing pulling up or pushing down. So what is normal force equal to here? Mass times gravity, exactly. So we just have to get this product here. So MA, so that's 10 times 2 plus coefficient of friction, 0.14, times the mass of 10 times G, which is 9.8. And then we just go ahead and run that through our calculator. Once we do so, we should get 33.7. And that's our tension force. Questions on this one? All right, let's move on. And let's do a different color too. Blue or green? Heard blue, that sounds good. This is where things get serious. You had to know this was coming. So for this question, we're going to be solving for acceleration. Take 2 minutes or so. See if you can get started on this. Take another minute or so. All right. Did anybody end up with 1.61 for an acceleration? A couple folks. Awesome. Okay, so let's go through this one together. If you didn't have time to finish, that's okay. We follow the same 4-step procedure with this that we've done for every other problem that looks like it. You can't have that on the test. You do have to know the procedure by heart. But I mean, the first 2 steps are force diagram and force equation. So hopefully you've got at least those 2 memorized. So force diagram, 9 kilogram mass is going to have gravity down, normal force up, tension to the right, friction to the left. For the 5 kilogram mass, we've got gravity down, tension force up. So, step 2, force equations. And these equations are only in the direction of each object's motion. So because the 9 kilogram object is moving horizontally, we're going to do a force equation that just takes into account the horizontal forces. So we've got tension force minus friction equals ma. And this little 9, so that I don't forget that's the 9 kilogram mass. For the 5 kilogram mass, we've got gravity down and tension force up. What is the important rule we have to remember when we do this? Very important rule when we do the force equation for the hanging mass. Exactly. Force of gravity is winning here. This block is going to be going down. So that means it must come first in the force equation. So that's step 2. We've got 2 steps to go. Step number 3 is to isolate tension force in both of these equations. So I'm going to do that over here by moving force of friction over to the right. And that makes it positive. Over here, I'm going to move tension over here to make tension positive. And then I'm going to move this MA to the left, and that'll make the MA negative. That's what I have there. So, final step is to set this equal to this, because they're both equal to tension force, so we're allowed to do that. So let's plug those numbers in. The only number that we shouldn't have is acceleration. So mass 9, so that's 9 kilograms times A, plus force of friction. Now, just like the last example, we're on a flat surface. Nothing's pulling up or pushing down. So friction is mu times normal force. And in this case, normal force is mg because there's nothing pulling up or pushing down. So mu is 0.3. M is 9 for this mass, and G is 9.8. So this whole thing is force of friction, and that's set equal to this guy over here. So force of gravity on the 5 kilogram mass is 5 times 9.8 minus the 5 kilogram mass times acceleration. And there's our equation. So now it's just a matter of getting these A's on the same side and getting all the other numbers on the other side, and then solving. So I'm going to shift this negative 5A to the left, and that'll make it positive. So 9A Thank you. Plus 5a is 14a. And that's going to be equal to this product minus this one. Because when I move this whole thing over to this side, it becomes negative. So 5 times 9.8 minus this product. I got 22.54. So again, I'm just taking this, and from that, I'm subtracting this product of 3 numbers. And so then to get the a by itself, divide both sides by 14, and I got 1.61. And that would be our acceleration here. There will be a question pretty much just like this on the test. So you do want to make sure you're practicing these. The good thing about practicing these equations and these problems is they're all the exact same. You solve them the exact same way. You're always going to be looking for an acceleration for these. Okay. Guess we should be environmentally friendly and do green next, huh? Okay. So the last page is going to be something where there are 2 different kinds of problems. And yeah, so there's 2 problems, and you have the option to do one or the other. So you get to pick which of those 2 you would like to do. So that's nice anyway. So last page, there's just 1 problem, and I think I want to go through at least one example. I'll give you 2 options. What do you feel less comfortable with? Do you feel less comfortable with something that looks like this, or less comfortable with something that looks like that? 1 or 2? Which should we go over first? 1? All right, let's do that. If we have time, we'll get through the other one. So there's some applied force put down on this object. Ultimately, that's going to be what we want to solve for. And that force is being applied at a 40-degree angle. Good part about all this is that there's no friction. So there's the setup. We know the angle, we know the acceleration, we know the mass. We need to figure out what that applied force is. I'll just give you 60 seconds. Try and get started with this, and then we'll go through the answer together. let's take a look at this. So step 1 is to create a force diagram. We're going to have gravity down. There's going to be normal force up. That normal force will be larger than gravity because we're pushing down, so the table has to exert more force to hold it up. And we've got a 40-degree angle. And because we're coming in at a 40-degree angle with respect to the horizontal, then when we draw this arrow coming out of the dot, that 40-degree angle will also be with respect to the horizontal there. So there's no friction, so there's nothing going to the right, so that's nice anyway. So if I want to figure out what my applied force is, that would be this guy right here. I'm going to need some more information about this little triangle. This applied force is headed in a couple directions. Part of it is going horizontal, we call that FAX. Part of it is going vertical, that would be FAY. But if I want to figure out my applied force, the only thing I have enough information to figure out is the applied force in the x direction. And the reason I know that is because I have an acceleration. This horizontal acceleration is going to help me figure out that applied force that occurs in the x direction. So, my force equation on this is just going to be applied force in the x direction equals ma, because there's nothing opposing its motion. So, I know the mass, I know the acceleration, and I know what them multiplied by each other is. 6 times 7 is 42, I think, right? Okay. So my applied force in the x direction is 42 newtons. So what that means then is that this side of the triangle is 42. Circle. So I know the adjacent side, I know the angle, and so I can use that to figure out what the hypotenuse is. And I'm going to use cosine for that, because we use cosine whenever we're dealing with an adjacent side. So cosine 40 is equal to adjacent, which is 42, over the hypotenuse, which is the applied force that we're looking for. So if I want to figure out the applied force, I'd multiply both sides by FA, and then I'd divide both sides by cosine 40. And as long as your calculator is in degree mode, you're going to end up with 54.8 newtons. And that's how you'd handle something like this. For these problems that are going to be on the back side, you're not going to have to worry about friction. So at least you've got that going for you. I'll just make sure that's true. Yes, there is no friction on those problems on the back side. So good luck on this tomorrow. You guys are going to do great. Have a good day, and hopefully your backs don't hurt too much from that shovel. See you later.